Have you ever stopped to wonder about the device you are using right now? It is a small marvel of glass, metal, plastic. It connects you to a world of information, entertainment, people. But this sleek, powerful machine did not simply appear out of thin air. Its story is a long and fascinating journey, a tale of human ingenuity stretching back over centuries. Computers today are an essential part of our daily lives, helping us work, learn, create, communicate. They feel so natural that it is easy to forget they were once the stuff of dreams and science fiction. They began not as pocket-sized wizards, but as colossal, clunky machines that filled entire rooms. This essay will take you on a gentle tour through the history of computer engineering. We will not get bogged down in dense technical details or complex equations. Instead, we will follow a simple timeline, pausing at the most important moments. It is a story of remarkable people, groundbreaking inventions, and quiet, steady progress. We will begin with the earliest mechanical calculators and trace the path to the smart systems shaping our present and future. Our journey is structured chronologically, like chapters in a book. Each era's key breakthroughs will guide us. We will see how one idea led to the next, each step making the next possible. From giant room-sized brains powered by glowing glass tubes to almost invisible microprocessors that drive our world. The evolution is astonishing. Better, faster, smaller. So let us begin. A 10-minute stroll through 150 years of change. Simple gears gave way to electrical switches, which shrank onto tiny chips, connecting the entire globe. Our story begins not with electricity, but with gears, levers, and steam. In the 1800s, the Industrial Revolution reshaped the world, producing a flood of numbers. Shipping logs, financial tables, scientific data. The work was slow and prone to human error. Charles Babbage imagined a mechanical solution. Calculations performed automatically with perfect precision. His difference engine was a massive device intended to produce mathematical tables. Thousands of precisely machined parts, all working like a magnificent clock. Though never completed in his lifetime, the concept was sound. His analytical engine was a true general-purpose computer in theory. Mill for processing, store for memory. Ada Lovelace, a gifted mathematician, saw beyond mere numbers. She realized the machine could manipulate any symbol, if represented logically. Notes, letters, more. Her detailed method is widely considered the world's first computer program. These steam-powered dreams planted a crucial seed. A machine could follow a program to process information automatically. Computation was about logical operations. The ideas lay dormant, awaiting new technology. A beautiful, ambitious failure that laid the groundwork for the electronic age to come. Time to turn the page. Let us jump forward. The 1930s, the 1940s, on the brink of global conflict. Fast, complex calculations became national security, code breaking, artillery tables. Electronics arrived. The key component, the vacuum tube, an amplifier and a switch, far faster than mechanics. In 1936, Alan Turing described a universal computing machine, defining what it meant to be a computer. Turing's foundations and wartime work turned theory toward practice. In 1945, Mauchly and Eckert unveiled ENIAC, 30 tons, a room of panels over 17,000 tubes. It dimmed city lights and was programmed by rewiring. Difficult, yet a triumph. It calculated 1,000 times faster than any human or mechanical device. Dinosaurs of computing, huge, powerful, groundbreaking, proof that electronic computation was possible. But tubes ran hot, failed often, guzzled power, and demanded constant maintenance. They were expensive, sustainable only for governments and large institutions. A change was needed. Smaller, more reliable, less power-hungry. 1947, at Bell Labs, Bardeen, Bratton, and Shockley created the transistor, a simple device in silicon, doing the tube's job as a solid-state switch and amplifier. Tiny, solid, efficient, using a fraction of power, little heat, far more reliable. Manufacturing matured through the 1950s, bringing widespread availability and new consumer devices. Second generation, transistorized mainframes arrived, smaller, faster, more dependable. IBM led the charge. Computers moved from secret labs into businesses and practical workflows. The age of room-filling giants was ending. The transistor solved reliability and power and pointed to miniaturization. Next up, solving the tyranny of numbers, putting a world on a chip. The age of integration. As power grew, so did parts. Wiring thousands of components was slow and fragile. A single bad joint could doom a system. The tyranny of numbers. The integrated circuit. Kilby at TI, Noyce at Fairchild. Pure genius. Make transistors, resistors, capacitors, and connections all at once on one piece of silicon. A monolithic chip, smaller than a fingernail. Tens, then hundreds, then thousands of transistors. Chips slashed cost, enabled complexity, and shrank size, changing everything. ICs powered the Apollo guidance computer, reliable computing packed into tight spaces. Gordon Moore observed transistor counts doubling roughly every 2 years, an industry-wide rallying cry. By the early 1970s, the CPU's essential logic lived on a single chip, the microprocessor. Intel's 4004, 1971, began in calculators, but its potential was far greater. Hobbyists and entrepreneurs built small, affordable computers. Grassroots momentum surged. Jobs and Wozniak's Apple I, 1976, lit the spark. By 1977, fully assembled PCs arrived. You could buy, plug in, and use them. Keyboards, screens, programs from cassettes, computing moved onto the desk. IBM's PC lent legitimacy. Engineering focused on accessible hardware, software, and peripherals. Personal computers transformed culture, writing, finances, gaming, learning to program. Yet most were still isolated islands of information. The next leap, weaving those islands into a web. By the 1980s, PCs were common in offices, schools, homes, but disconnected. ARPANET technology matured in military and universities. In the 1990s, the internet opened for public use, powerful but unfriendly, arcane commands and text tools. Berners-Lee's World Wide Web used hypertext plus 3 pillars, URL, HTTP, HTML, giving the internet a graphical, intuitive face. Browsers like Mosaic and Netscape ignited an explosion of content. Companies, universities, individuals rushed online. Engineering focus shifted to global infrastructure, servers, routers, fiber optic backbones, and complex service software. As the century turned, desktops ruled, but miniaturization and efficiency marched on. Phones gained cameras, music, and basic internet. The next platform arrived. The 2007 iPhone fused design, a mobile OS, and multi-touch, creating a true handheld computer. With Android, smartphones became ubiquitous. Engineers built power-efficient systems on a chip integrating CPU, graphics, memory, and more. The cloud offloaded storage and heavy compute to vast data centers. Streaming, email, social apps run on remote servers. Today's architecture blends smart endpoints with powerful cores, our connected world. Now the pace is faster than ever, driven by an explosion of data, social feeds, and scientific sensors. Understanding data fuels AI and machine learning. Specialized chips, GPUs, TPUs, run many simple calculations in parallel for AI workloads. Further ahead, quantum computing. Unlike bits of 0 or 1, qubits can be both, promising breakthroughs in fields like drug discovery and materials. The pattern repeats. An idea emerges, a new technology enables it, engineers build it. Smaller, faster, cheaper, more powerful. Today's challenges: fair and transparent AI, securing data, and slashing energy use. The story is far from other. The next generation will write new chapters. The future will be fascinating to watch.